Thank you for coming. My name is Vanio Markov. I will talk about our research in the area of quantum stochastic generators in collaboration with the business at Wells Fargo and IBM research. The problem we are solving with this research direction is by given sequences from some non-stationary stochastic process to find a model which predicts the future distributions. We are focusing on particular case, specific case of sequences generated by a market process called mid-price of a limit order book. Limit order book is two-sided queue which keeps the incoming buy and sell orders for security on any electronic trading exchange. The mid-price is the average between the best buy and the best sell offer at any moment of time. The mid-price is very important statistic for any trading, automatic trading algorithm. So there are many attempts it to be modeled. The difficulty comes from the fact that it is very high frequency statistic. It can change, it changes on nanosecond scale. It means every nanosecond it can change several times. We are approaching this problem through quantum modeling, and we have reason to do that, and I will discuss the reasons. You're using the theoretical apparatus of quantum operations, general measurement, POV measurements, and dilated unitary systems. We built our hypothesis space in the set of unitary operations with mid-circuit management, unitary circuits with mid-circuit measurement, and search in this space using evolutionary search algorithms and quantum ansatz optimization methods. The structure of a simple quantum hidden Markov model is shown. In general, it contains state system, measurement system, unitary, which entangles the state system and measurement system, and measurement, mid-circuit measurement, and reset of the state of the circuit, and then you repeat the step. Sorry. Why we think the quantum approach is promising for this very challenging task? There are several, at least three main reasons. First, we have proven that the space, the Hilbert space to model particular stochastic process is quadratically smaller than the classic vector space necessary to model the same process. So if the classic vector space has 256 dimensions, for example, the Hilbert space will be somewhere around 16 dimensions. This is huge decrease of the dimensionality and the degrees of freedom, and the learning algorithms in this case are significantly more efficient. The second reason is that there is a continuity between the search space in the space of the hypothesis, in the space of unitary circuits, to the distributions generated by the quantum operations. It means small changes in the unitary causes small change in the generated distribution. This is fundamental condition for smooth search space and good optimization processes. And third, these first reasons are related to the learning of the quantum models. The third reason is related to using the quantum model for prediction of distributions. When we roll forward quantum model to the quantum model to predict particular distribution, the convergence is very important. Actually, we are running a Monte Carlo experiment, Monte Carlo simulation, in order to generate all the distribution generated by the model. Again, there is this is work in progress, but there is expectation the convergence for the quantum model to be quadratically faster than the convergence for the classic model, simply because the base of the model, the state transition system of the model, is a quantum Markov chain. And it is proven that the quantum Markov chains are quadratically faster in convergence than the classic Markov chains. This is here is very simple example. On the left, you see a classic model, hidden Markov model with 4 states. Then you see the distribution. It generates sequences over 4 symbols. Here you see the sequence distribution generated by this model. And on the right side, you see the corresponding quantum circuit which simulates the model. This circuit has just one qubit. The top qubit is the state qubit. The next 2 qubits simply simulate the outcome, because there are 4 outcomes. We need a 4-dimensional system to generate the outcome. So you see this relatively, the 4 states, the 4 classic states are simulated by just 2 quantum states. This is the main reason to use this type of models. This is very briefly the case, very simple case of the process we are trying to model. In the middle, the state transition diagram for a classic market model. Intuitively, every market has bare state, bull state, and 2 transitional states. In every state, we have biased symbol generations. The market goes up or the market goes down. The distributions are biased by this particular state. This is the process distribution generated by this simple market example. And this market example has 4 states. It cannot be reduced anymore. At the end of this talk, I will show that this market model can be generated by quantum model with only 2 states, quadratically less. Again, just the setup. We have linear transitions with linear stochastic operator of the state, and we have linear symbol generation with linear emission matrix B on the observations. Our view to the quantum implementation of the hidden Markov models, there are 2 views. The first view is based on the hidden Markov model represented as a quantum operation, especially as a positive operator valued measure operation, which has components corresponding to the observable symbols. This is the pure, nice mathematical representation of the process. When we apply the full operation, tau in this case, one of the components, any of the components can be successful with the probability. Symbol generation process is the probability describing the probability of success of particular component, and the new quantum state is described on the next line. Now, what is happening? You apply this operation over the quantum state, the system transits from one state to another, and then a symbol gets generated. And this is exactly what we are interested in when we model the process. Now, the probability of a sequence is the trace of this composite operation on the bottom. So everything looks great. Just one problem: learning in the space of the quantum operations is not, let's say, is not well defined. First, the quantum operations per se are not physically implementable, so there is no physical machine that implements this operation. Second, a quantum operation in general is a very general, with small restrictions matrix. So learning in the space of all the matrices with dimensions, for example, 10 by 10 is a very tough operation. So we need to move to another space which allow us to parameterize the model into unitary operations represented by unitary gates, where we can implement the outcome with existing quantum computers, and we can learn more efficiently. So there is a second view, equivalent view to the same process. This view is a unitary representation of the hidden Markov model. The unitary representation can be inferred from the operation representation, POVM representation, using process of dilation. Actually, these 2 representations are equivalent. You can move from the left to the right and the right to the left. I discussed the left side. The right side is derived by dilation. To the system on the left, you have to add additional quantum system called emission quantum system or auxiliary quantum system with dimension depending on the number of the observations. And then you have to build a unitary that entangles the systems, and then you apply the projective measurement on the measurement system, and you get exactly the same behavior as the first system. But here on the bottom is our design we use for our experiments of a quantum hidden Markov model. As you can, we are learning the unitaries. As you can see, every unitary first entangles the state with the observation, and then we measure the observation system. When we measure the observation system, the measurement subsystem collapses. This collapse is reflected to the state system. Then we reset the measurement system and we go to the next step. Here is how we learn these things. On the input of the algorithm, we have a sample set of sequences generated by some natural process like market or just some classic generator. We have the distribution, we call this target distribution. In this case, I have called this M distribution. We have to compare the distribution generated by each circuit in our search space with the target distribution. We define the divergence measure between the two distributions, and our search algorithm tries to optimize the divergence measure to find a unitary which minimizes the divergence measure to particular level. This is the probability or the divergence. We are estimating the target distribution by our model. How do we do this? We use a evolutionary algorithm. We initialize a space of unitaries. For every unitary, we estimate the divergency. Then part of the unitaries with good divergency, low divergency are selected. They're modified using modification operators. In this case, modification operators are mutation of the circuit and recombination of the circuit with another circuit. And then part of the new circuits is selected for the next generation, again through estimation of the divergency. Why this thing works and why the search in the space of unitaries drives properly the minimization of the probability is described on the left. Why does it work? If you look at the delta of the norm of the unitary operators in the search space, and if you look at the norm of the quantum operations, actually the norm of the quantum operations is close to the distribution generated by the quantum operation, you see that the change in the norm of the distribution is restricted by change of the norm of the unitaries. It means that small changes in the search space trigger small changes in the space of the fitness of the search, which is guarantee for the success of the search. And in the end, our initial example with the market hidden Markov model with 4 states can be modeled by this one state system. As I said, the second, 2 state system, but 1 qubit system. As I said, the second qubit is used for measurement only, and it is reset at every step. And this is on the picture, on the graph on the right, you see the success of the learning process. And now Vlad will explain the IBM's approach to the process. You have the...
So mic check. Good. So thanks, Vanio. Let me switch to the next slide. So my name is Vlad Rastunkov. I'm from IBM. And one thing I wanted to mention very briefly is that all of the results are available in the preprint. So if you search for quantum hidden Markov models, you will find it. It was announced yesterday. So very quickly, before we ran our test examples, we wanted to make sure that that the design of our circuit is correct. So we first started with the test case. So in this case, we're not training anything. We are making sure that all the representations work exactly the same across channel representation, across circuit representation, as well as on the hardware. For such use case, we selected a well-known model for amplitude damping noise, which we call amplitude damping process. And so we simulated that in using the 3 methods. So obviously the first 2 fairly clear, so we know from textbooks what the circuit representation is for the amplitude damping noise channel. And then for the hardware runs, we used IBM Montreal device. And we actually tested out the capability of using sampler primitive that was announced earlier this year by IBM. When you run the primitives, you get the benefit of having error mitigation and error suppression techniques also available to you. So we use dynamic decoupling behind the scenes as well as M3 mitigation technique. Results matched very well across wide ranges of gamma parameter, as shown basically by the chart on the right-hand side. So the way you read this chart is on the y-axis you have the probability of a particular sequence, and the x-axis shows like particular sequences as measured by the circuit. So going forward, as Vanio described, the second approach is to come up with some ansatz that we can train. So in this particular case, we considered another state system, which is presented in one of the first papers on hidden quantum Markov models. And then we try to learn this process by implementing heuristic ansatz. So what heuristic means, of course, is maybe not the most optimal one, but it's a practical something we can implement today. And we used real amplitudes and efficient SU, so special unitary 2. So we have 3 circuits, but essentially the last 2 are all efficient SU ansatz. So they are parameterized, and as shown here, and then our goal is to optimize those parameters as we, as Vanio described, we have a quality measure between the 2 distributions. In this particular case, the best model turned out to be the most complex one, the efficient SU ansatz. We also compared different entangling strategies. It happens so that the full entanglement is only marginally better than linear entanglement, which in our case allows us to use linear entanglement because it's easier to implement on the hardware. Initial state preparation is something of a separate topic, but we found that maximum mixed state is a good starting point. In this particular example, actually in the second one as well. In some cases, you would need to use another variational circuit to optimize like what your starting state is, and that's what we use and mentioned in our algorithm as well. And then the third test case, where we compared again the 3 approaches, is the simple market model as Vanio has described. Where we have 4 states, and then we again use those heuristic ansatz. In this case, all of the ansatz circuits were giving approximately similar results. So we chose the simplest one, which in this case is the real amplitudes. But the other benefit of looking into this is we have only 2 parameters to optimize, so we can actually look at the optimization landscape, which is really, really simple in that case. And if we explore it a bit more, we even see that out of the 2 gates we have for our ansatz circuit, only 1 is actually non-identity gate. So the upper one are Y rotation. So essentially it's just optimization with 1 parameter, whereas in the classical case you have 4 parameters that you need to optimize. And I think that brings us to sort of a set of conclusions and future directions. So just to summarize, as Vanio described, by looking at those examples and the theory, we identified that in quantum hidden Markov models, we have a smaller state than in the classical case. We compared results across hardware and simulations using different representations. And then for the future directions, what we are planning to investigate a bit more are essentially looking into the observed sequences in the practical use cases, which may have more hidden states. Vanio talked about the limit order book, so we may take some of the examples inspired by that data set, as well as we are planning to discuss a bit more on the side of the inference. So today we were mostly interested in how well we can feed and model the process, but in the future, how can we extend that to the new length of the series. So thank you very much.